Hello everyone, welcome back to Nated Engineering. We are still doing Heat Engineering Science N3, and today we are going to look at a question paper that was written on the 30th of November 2015. We are going to start from 5.1, which says define the specific heat capacity of a substance. A specific heat capacity of a substance is the heat energy that is needed to raise 1 kg of that substance by 1 degrees Celsius. And we move on. 5.2. They say determine the mass of silver. When silver is heated up to a temperature of 120 degrees Celsius and then placed in a container with 20 kgs of water at 50 degrees Celsius. The final temperature reached by the silver in the water is 60 degrees Celsius. Use the specific heat capacity of silver as 0.2 kilojoules per kg degrees Celsius. Now, as to calculate for the mass of silver, we are given T1 of silver is 120 degrees Celsius and its specific heat capacity is 0.2 kilojoules per kg. We are given the mass of this is silver and this is water. We're given the mass of water is 20 kg. The temperature, which is T1, is 50 degrees Celsius. And the specific heat capacity, there is a table on the question paper which has specific heat capacities. So the specific heat capacity is just a matter of going to that table, looking for the specific heat capacity of water and then extract. We are then given T2, which is the final temperature of both the silver and the water. We know heat energy lost by the silver is equals to heat energy gained by the water, because you can see that silver had a higher temperature compared to water at the start of the process. So we are going to say Q lost by silver is equals to Q gained by silver. The Q lost is equals to M of silver times specific heat capacity of silver times the change in temperature of silver. And the Q gained will be mass of water times the specific heat capacity of the water times the change in temperature of that water. So we're looking for the mass of silver, which is MS. We're going to substitute the other ones. Specific heat capacity of silver is 0.2. Change in temperature is 120 minus 60 is equals to 20 times specific capacity is 4.187 times the change in temperature, which is 60 minus 50. This is the only unknown, and that is exactly what we are looking for. So we're going to divide both sides by 0.2 times 120 minus 60. Okay, going to divide both sides. Here we are going to have a cancel out, and here we will end up with something like this. Mass of silver is equals to 20 times 4.187 times 60 minus 50 divided by 0.2 times 120 minus 60. And this as will give us the mass of silver as, according to my calculator, 69.783 kgs. And then we move to question 5.3. They say a rectangular steel plate of a steam boiler has measurements of 1.5 meters times 1 meters. As the steam boiler is heated, its temperature increases from 20 degrees Celsius to 280 degrees Celsius. The coefficient of linear expansion is 34 times 10 to the power negative 6 per degree Celsius. And then they say determine the final area. This is the information that we are given. We are given the area and we are given linear expansion. We are asked to calculate for the final area. We know that the formula that we use to calculate for the change in area is original area times coefficient of linear, it's coefficient of area expansion times the change in temperature. And we know that the coefficient of area expansion is equal to 2 times the coefficient of linear expansion, which is what we are given in this case. And the temperature difference, we are told that its temperature increases from T1, which is 20 degrees Celsius, to T2, which is 280 degrees Celsius. This is T1, this is T2. Then the change in temperature is 280 minus 20. So we are asked to calculate for the final temperature, for the final area rather. The final area will be equals to the original area plus the change in area, which is why we have to calculate for the change in area. So we're going to do exactly that. Let's take this formula, right? So we are coming to this formula now to calculate. The original area is what? Is length times breadth. That one we know, which will be 1.5 times 1. That is our original area. What is the coefficient of area expansion? Is 2 times the linear coefficient of expansion. We are going to have 2 times 34 times 10 to the power negative 6 times change in temperature. Here, change in temperature is 260 degrees Celsius, which will be 260 degrees Celsius. What is the value of the change in area? According to my calculator, is 0.0265. So we are going to have, because the original area is 1.5 times 1, which gives us 1.5 meter squared. Therefore now this is also meter squared. The original length, which is 1.5 times the change in the original area rather, plus the change in area, which is 0.0265, and the final area will be 1.5265 cubic meters. That will be the final area. The final area is equals to the original area plus the change in area. 5.4 reads as follows. Steam is developed under pressure of 760 kilopascal. So we are dealing with the pressure of 760 kilopascal. They say, and wet steam is formed with a dryness fraction of 0.95. So basically here we are generating steam, and they're telling us, since we know that the first steam that is produced is wet steam, they're saying we're having a pressure of 760, and the first steam, as we all know, it's wet steam with a dryness factor of 0.95. And then we continue. They say this wet steam now flows to a superheater where it is dried and superheated to a temperature of 200 degrees Celsius. That is the temperature of the superheated steam. How do I know? Because it is a temperature that is higher than the saturation temperature. If you can go to the steam table, look at 760 kilopascal. And we know how to read the information from the steam table. We did that on the previous video. Look at the saturation temperature, which is written TS under 760 kilopascal. You will see that the saturation temperature is 168.3. So now we're having 200 degrees Celsius. It tells us that that is the temperature of the superheated steam. They say use the specific heat capacity of the superheated steam as 2.6 kilojoules per kg degrees Celsius. Question number 1. They say calculate the enthalpy of 1 kg steam of the following. Question number 1, which is 5.4.1, the wet steam. Question number 2, the dry steam. And then they say the required superheating of dry steam. So this is the temperature that we are this is the data that we are given, information that we are given. We're given the pressure, which is 760 kilopascal. We're told that the dryness factor of the superheated steam that is first formed is 0.95, and then after that steam is superheated to a temperature of 200 degrees Celsius. So we're asked to calculate for what? The wet steam, which is 5.4.1 is H wet. We know it is given by what? HF plus XHFG. We go to the steam table to extract these values. We know how. 760. Under 760, I got that the value for HF, it is equals to 712 plus we have the dryness factor, which is 0.95 times HFG. Under this pressure, which is 760, my HFG, I got that it is equals to 2054. And then this, according to my calculator, is equals to 2663 kilojoules per kg, because we are working with a mass of 1 kg. So if it was 2 kg, we're going to say times 2 here, and then we say it's just kilojoules. So we go to the next one. It's 5.4.2. They say dry steam. Dry steam is Hg. So this is a matter of going to the steam table, extracting the value, and put it here. 284. That's the wrong value. It's 2766. Sorry about that. It's 2766 kilojoules per kg. So we go to the next one. They say the required superheating of a dry steam. Here they are looking for the heat energy that we added to the dry steam, turning it to superheated steam. So remember, the formula to calculate superheated steam is H sup and it is equals to Hg plus specific heat capacity of the superheated steam, T sup minus Ts, which is the saturation temperature. This is what they are asking for. They want us to calculate the heat energy that we added for the steam to have a temperature of, or for the steam to be superheated with a temperature of 200 degrees Celsius. So we can just from here take this and say that is, they say is HSS. That is the HSS that they are looking for. But looking at the marks that they are giving us, which is 4 marks, it tells us that they are expecting us to use this formula that says H sup minus Hg. Not to say that you are not going to get the same thing if you were to use this, but the marks, it's 4 marks, we are supposed to go this way. So first of all, we are going to calculate the enthalpy of the superheated steam, which is the whole thing, and that is going to be Hg, which is 2766 plus the specific heat capacity, which is 2.6 in bracket. Saturation temperature is 200. Oh, it's the superheated temperature, sorry. Then the saturation temperature. The saturation temperature we are going to get from the steam table, the one that is labeled TS. Under, it should correspond with the pressure of 760 kilopascal. And I extracted the value, and the value is 168.3. You should also go to the steam table to double check these values, because I'm also human, I do mistakes. So the answer, H sup, I got that it is equals to 2848.42 kilojoules per kg. And then the HSS, which is the heat energy that was added to the dry steam, turning it to superheated steam with a temperature of 200 degrees Celsius. The formula is H sup minus Hg it's going to be 2848 minus 42 0.42 minus our HG, which is 2766, and I got that my answer, or our answer from here, is equals to 82.42 kilojoules per kg. Take this and put all the values. Put the specific heat capacity of the superheated steam, the saturation temperature, the superheated temperature and the saturation temperature. You will see you are going to get this value, exactly this value. The reason why I went this way is because of the mark allocation, which is 4 marks. I doubt that if we were to put it here and just calculate, they were going to give us the full marks. So yeah, the reason why I went this way is because of the mark allocation. That brings us to the end of our question. I will see you on the next video.